All right. Good morning again, everyone. Kumusta po? Sorry I wasn't able to meet you anytime last week. I was really down with sore throat and flu. So kahit ng sore throat, I cannot talk. So yeah, I decided not to meet you. But I guess you were able to finish homework or the homework in Module 5, which is a barrage of basically just definitions of regarding matrix inverse, adjoint, and then a bunch of norms of vectors and matrices. So probably let's begin there. Do you have any questions about about that module, or any serious typo that you encountered? Any clarification? Wala naman po. But how was homework 5? Sir Dexter, you want to say something?
No, sir. I was just saying I have seen no errors so far, and homework 5 is manageable compared to homework 1, 2, and 3.
Of course. Homeworks 1, 2, and 3. Yeah, admittedly, it's on another level. And yeah. And as you have seen, medyo sana gumaan yung homeworks along towards the end kasi I had different expectations when I handled the class. It's not your fault. It's what was given to me. So that's how I designed, or that's how I intended to design, of course. But unfortunately, for those who hope that I will follow the outline and of course description, I need to deviate uh, not just by a little bit, but a lot, just to make this course enjoyable to everyone. So I hope that's fine. All right. So pero kumusta naman? I think we have just a full week to go before the end of classes. End of classes, I think, is on August 9. So for module 6 that I just uploaded um, yesterday, late yesterday or early today, I have 3 problems there. Though there are only 3 problems there, still long, but yung pagiging long niya is about the mechanical processes. Uh, you will spend more time doing it than thinking about how to do it. It's not like proof questions wherein you have to spend half a day thinking about the solution or even a day, but you need to sit down and perform the operations or perform the instructions carefully. Um, and then it might take some time, but at least it's mechanical this time. So yeah, just a heads up because the deadline I think that I wrote in the module is when I think it's in August. If I'm not mistaken, it's August 6 or 7. Kindly double check. Pero you'll have that to be the final homework. And then the deadline for all other requirements that you haven't submitted yet would be on August 9th. All right. That's the last day of classes. So hopefully by August 9th, I get all of the pending homework so that I can start grading and compiling all your work. And then um, I will give the last homework on August 9. That would be homework number 7. And then hopefully I will not be flooded with submissions kasi I've seen some of the problems medyo 30 plus na yung nakapag-submit. So if all will flow according to my plan or to my expectation, once you submit the final homework, then give me a couple of hours to take a look over it, and then I can also upload in Moodle your final grade. All right, and then you'll have probably I'll give you a couple of days to think over the grade that I gave you, and then if you have some questions, you have some appeals, just let me know. But I will only entertain questions and appeals until the deadline for the submission of grades. I'll check the dates, but that's the last time or the last day that I'm going to accept some questions about the grades or the conversion from your raw scores to your final grades. And then yeah, but I'll try to give the final grade or issue the final grade to you at least unofficially couple of hours after you submit homework 7. And then I will upload everything officially to the UPOU portal, probably yeah, at the end of at the deadline, the last day of submitting grades. So para meron kayong days to think over the grade that I gave you, and if you don't think you deserve it, just let me know. We can talk about it, but do it as soon as possible. All right. So ayokong wag sana tayong I mean, lahat ay mag-consult about the grade near the end of the grading period, or the last day for submission of grades, right? Any concerns? I hope that won't interfere too much with your other class. I promise homework 7 would be the easiest one, so don't worry about it. For now, focus on the other requirements that you have not yet submitted, especially for those who took advantage of the long deadlines for everything. There's still a lot who were not able to submit problems for homeworks 1, 2, and 3. So prioritize that. Of course, do problem 6, homework 6 first. It's easier, I guess, than 1, 2, and 3. And then, but after that, do not do not think about the final homework yet. Just make sure you finish 1, 2, and 3. Because I promise homework 7 will be the easiest one. You can do it in a day. So yeah. And then I can grade it, the entire homework. It's just a one full submission. And then I can grade it in a couple of hours. All right. So any questions? I hope that's fine. I hope it won't interfere too much with your other class or your other activities for the week. So yeah, medyo yeah, medyo patapos na yung semester, so try to finish all the pending requirements, all right? Okay, any reactions, any questions? All right, done? About Module 5, because my plan is, if you don't have any question about Module 5, I'll just go over the definitions that they need for starting Module 6. All right. So i-review ko lang yung mga terms from Module 5 na mamimit natin sa Module 6. So if you have some clarificatory questions about homework 5, please raise them, because I will not go over the entire module. Okay. All right, so if none, then let's proceed. So I have here open module 5. Let's start with definition 14. The definition 14 just gives us the meaning of what the complex conjugate of a number of complex number z is. So if you have a complex number a plus bi, right, the conjugate of z, denoted C star or Z bar. I don't know if sometimes I used C bar, but that's another commonly used notation. I was initially hesitant to use Z star because I don't want it to be confused with the adjoint of a vector, right? But so that's why I initially wrote the module using Z bar, but I decided to introduce C star anyway. So another abuse of notation, but that should be fine. So the complex conjugate is just the complex number whose imaginary part was negated. So if you start with a plus bi, its conjugate is a minus bi. So all you need to do is to negate the coefficient of the imaginary unit. Okay. It is denoted by C star or again by Z bar. Okay. And then analogous to that, we define the adjoint of a matrix. So if you have a matrix A whose entries are Aij, so again, this notation means that you have entries, or the entry on the ith row and the jth column is A sub ij, right? So it's an m by n matrix with complex entries. Then the adjoint of A, we denote it by A star, is the matrix whose entry on the ith row and jth column is the conjugate of A sub ji. So meaning parang tinatranspose nyo yung matrix, but after transposition, you're taking the complex conjugate of each of the entries. Okay. So I guess in the supplementary material, I included the concrete example for the adjoint of a matrix. All right. So that being said, don't forget the transposition. Okay. Yung nasa ith row and jth column of the adjoint is the conjugate of the entry on the jth row and ith column of the original matrix. Again, to find the adjoint, transpose nyo muna siya, and then kunin yung conjugate ng bawat entry ng matrix. All right? So that means if you start with an m by n matrix, then the adjoint would be n by m because you do the transposition first. Okay? Now, if it so happened that your matrix A is equal to its conjugate or its adjoint, or sometimes we call A star also as the conjugate of the matrix or the complex conjugate transpose of the matrix, all right? So if A is equal to A star, then we say that the matrix is Hermitian, okay? And Hermitian matrices are the generalization of symmetric matrices for matrix with real entries. Because again, if you have a real number, so if you have a real number R, its conjugate, its complex conjugate is equal to itself, right? Because you can write R to be just A plus 0 I, and so R star would be A minus 0 I, which is still R, right? So the conjugate of any real number is itself. So if you have a matrix A whose entries are nothing but real numbers, then its adjoint is just the transpose, right? So A star will just be A transpose. And so if your matrix has A star equals A transpose, so it is Hermitian in general, but if it is purely of real entries, then it reduces to the usual symmetric matrices that we know, right? I guess I mentioned all those stuff here in this paragraph, so that's fine. Okay. And in definition 15, we talk about the inner product. So I just defined the inner product to be the Euclidean inner product, but there are other inner products that you can define for any vector space. All right, but let's focus on the L2 inner product or the Euclidean inner product. And I did not introduce any other inner products here, so that's why I just called it the inner product. But in case you will go into more abstract linear algebra, you will encounter different kinds of inner products. But here, when I say inner product, it is just this guy, all right? So if you have two vectors coming from Cn, say x1 until xn, then the inner product for us of x and y, denoted sometimes by angular bracket xy, or sometimes by just this guy, is exactly this. It's the product of the adjoint of x and y. And if you want to get the formula for that, or to write a more explicit formula for that in terms of the entries of your vector, it's just the sum of the products of the conjugate and the entries of your respective vectors. Okay. So this is how we define inner products. So parang siya yung generalization ng dot product na alam nyo from matrix arithmetic, all right? So it's a dot product of what? It's a dot product between the vector of, which is the complex conjugate of the given vector and the first vector times the second vector. So dot product lang siya, pero yung unang vector na gagamitin nyo sa dot product, kukunan nyo ng conjugate muna, yung bawat entries niya. Alright? So, I don't think this will matter too much in the exercises or in the homework, because in Module 6, we will just be dealing with real numbers. But I still opted to include the definition for complex numbers, just in case in the future you will work with complex numbers. All right? So the main point here is that if you have two vectors, and if you compute the inner product of those two vectors, then what you'll get back is another complex, is a complex number, right? So x and y are vectors coming from Cn, so they should have the same length. If you take their inner product, you will get back a single complex number. All right. Okay, and then here I went on defining what the Euclidean length or the L2 norm of a vector x. So this is the usual Euclidean length that we know. So it's denoted by norm sub 2. So the L2 norm of x is just the square root of the inner product between x and itself, right? So this is the inner product of x and x. So you can write it as this in bracket notations. And it's just the square of the magnitude of each entry, then take the summation, and then take the square root. All right? So your usual Euclidean length for complex vectors. Okay, I defined here the angle, but I won't need the angle here later. So theorem 37 gives us some properties of the inner product. Specifically, it's a bilinear operation. So I hope you read that already. Crucial thing for us in this is definition 16. Definition 16 defines the orthogonality between two vectors. So if you have a pair of vectors x and y, they are orthogonal if their inner product is equal to 0. Okay? So if you take x star y, x star times y, you get the complex number 0, then the two vectors are said to be orthogonal. All right? So orthogonal because, or sometimes we say that they are perpendicular, because if x star y is equal to 0, and we revisit the formula for the angle between two vectors, so this if x and y are orthogonal, then this inner product goes to 0. So we get cosine theta equals 0, and then theta must be 90 degrees, right? So that means that's why it's called orthogonal or perpendicular, because if the inner product is 0, the angle between these two vectors must be 90 degrees or negative 90 degrees. So that's where the name came from. So orthogonality, again, our test is the dot product or the inner product. If the inner product is 0, then they are orthogonal. Then we say two sets are orthogonal to each other if and only if any vector from x is orthogonal to any vector from the set y. Okay, so that means if you draw any element from x and any element of y, and they are orthogonal, then that means that the two sets are orthogonal. And then specifically, if a set is orthogonal, if all of its elements are pairwise orthogonal. So if we say that a set X is orthogonal, we are saying that X is orthogonal to itself, meaning that it is orthogonal to all other vectors in the set. So another way to check that is to get any two element of X and check if they are orthogonal to each other, okay, provided that they are not equal to each other. Okay? So pagka meron kang set X, kumuha lahat ng element ay orthogonal sa lahat ng iba pang elements dun sa set, then your set X is orthogonal. Okay? So sa sarili niya lang siya hindi orthogonal. All right? And finally, a set X is said to be orthonormal if it is orthogonal and the length of each vector in X is equal to 1. Okay? So that's where the normality or the suffix normal came from. So orthogonal siya na normal lahat ng elements. Okay? Okay, theorem 38 is fun because it guarantees linear independence of the vectors in an orthogonal set. But in the addendum to the module 5, I guess I gave an example that the converse is not true. Meaning if you have a linearly independent set, then the elements are not necessarily orthogonal to each other. Okay? So kapag ka orthogonal set, automatic na linearly independent. Pero pag linearly independent yung set, hindi automatic yung orthogonality. Right? So for instance, I guess this is the example I gave back there in the addendum. The set B consisting of 1, 0, 0, 1, 1, 0, 1, 1, 1 is clearly linearly independent because we know that this is a basis for R3. However, if you take 1, 1, 0 star times 1, 1, 1, so we take the inner product between 1, 1, 0 and 1, 1, 1. This is just 1 times 1, that's 1. 1 times 1, that's 1. Oops. And then 0 times 1, that is 0. So the answer is 2. So here we have an example of a linearly independent set, but it's not orthogonal. All right. Now, why do we want orthogonal sets? Orthogonal sets are the best basis, or are the best bases, because they tend to be more stable than bases that are not orthogonal. All right. So one quick example of an orthogonal basis is the elementary basis, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Those three vectors are orthogonal to each other, all right? And they form a basis. So that's why it's an ideal basis, because it's orthogonal as well. It is a basis, and it's also normal. It's an orthonormal basis, actually, because the length of each of the elements of the elementary basis is of unit length. All right. So that's theorem 38. Okay. And a corollary to that is an orthogonal set of X members of an orthogonal set X of N members is a basis for C to the N. The proof should be simple. A set X is orthogonal, so it's automatically linearly independent, right? It has N members, which is equal to the dimension of Cn. So any linearly independent set with number of members equal to the dimension of your vector space is automatically a basis. Okay. And then I'll also need definition 17 for module 6. This defines what a unitary matrix is. So if you have a square matrix with complex entries, say Q, and this will become unitary if and only if Q star Q is equal to Q star is equal to IN. So that means that the multiplicative inverse of Q happens to be its adjoint. So if Q star, or the adjoint of Q, is equal to Q inverse, so that means that the matrix Q is unitary. Right? And it's nice because taking them, computing the inverse of a matrix is a very computationally expensive and unstable process. So it will be nice if there's if we can have an easy way to compute the inverse of a matrix. And if you have a unitary matrix, then computing its inverse is not a problem, because you just need to find its adjoint, which is just a transposition of the matrix and then taking complex conjugates of the entries, then you get yourself the inverse right away. So that's why in most algorithms in solving linear systems, especially the big linear systems, say 100,000 by 100,000 matrix, coefficient matrix, we always want to have a unitary matrix at hand. So because computing the inverse there will not be a big problem. Okay. All right, then I just elaborated why unitary matrices are good. Specifically here, if you have a matrix Q with columns Q1, Q2 until Qn, if you get the adjoint Q star, so it will be this matrix, okay? Yung mga columns, sila ngayon ang magiging basihan para mo compute yung mga rows ng adjoint, right? Because adjoint is just the transpose, and then you take the conjugate the complex conjugate of all the entries. So Q star will be the matrix whose rows would be the adjoints of the columns of Q. So kaya naging ganito siya. And then if you multiply it with Q, and then take the expanded form of the right-hand side, we get this guy. Okay? And then since we assume that Q is unitary, so Q star Q must be equal to the identity, so we got this. And then what can we say? We can now compare entries, all right? And see what can we say about each of the entries. Well, Q1 star Q1 is equal to 1. So that means that, oh, but what does this represent? Do you remember? What does the inner product of a vector to itself represents? Or what will that give us? Anyone? Ano nga ba itong ibibigay sa atin ng quantity na to? We know this is a real number, right? Because this is just the inner product of Q1 with itself. That's Q1 inner product with itself. So, but do you remember what this quantity gives us, or what can this quantity give us? So I hope you're just too shy to answer, right? But this is actually the square of the L2 norm. Right?
Norm of 2, sorry.
Okay, that's fine. So basically, yeah, if you take the inner product of a vector to itself, you get the square of its L2 length, right? So that means Q1, Q1, or Q1 star Q1 is equal to 1. That means, that tells us that column Q1 has Euclidean length equal to 1, the square root of 1, right? So ang length ng Q1 ay equal kay 1, okay? And then let's move on. Q1 star Q2 will be equal to 0, kasi 0 yung entry dito. Q1 star Q3, which is somewhere here, will be somewhere here on the left side, so 0 din siya, until you reach the end, which is Q1 star Qn, 0 din siya. So what does that tell us about Q1 relative to Q2, Q3, Q4 until Qn? Any observation? Oh, yes. Sorry, I can't see who's raising his or her hand. Yes, Ma'am Rina.
Sir, the product is always 0 except for the first element, yung Q1, Q1.
Yes.
This
Pero, yes, ano po yung pwede nating i-conclude mula dun sa pagiging 0 ng inner product against any other element?
Sir, merong
Is
multiplier.
always the identity matrix.
Yes, Jen, yung identity matrix ay nasa left. Pero I just want to go back to Ma'am Rina. Ma'am Rina, so tama, yung inner product from of Q1 against Q2 until Qn ay lahat 0. And what conclusion can we make out of that?
Sir, may multiplier po tayo na, yung sum po nila would be 0. So, malamang po, sir, ay additive inverse yung mga elements na ina-add natin.
Okay, for para dun sa mga elements nila, right?
Yes.
Yeah, but yeah, simple, medyo mababaw yung gusto kong sagot, but anyway, yeah, that's true, but the answer I'm looking for is that Q1 is orthogonal to the other columns. So medyo nag-overthink yata si Ma'am Rina, but that's fine. Because the inner product of Q1 against Q2, Q3, Q4 until Qn are all 0, that means orthogonal. So if you have a unitary matrix from this analysis, we can see that its columns are orthogonal to each other. So yun yung kagandahan about unitary matrices, not just about the economy of computing their inverses, but also the nice property, the linear algebraic property, that the columns are orthogonal to each other. Actually, hindi nga lang orthogonal kasi if you look at the diagonal entries nito puro 1 sa kaliwa. If you look sa kanan, yung diagonal entries will be the squares of the lengths of Q1, Q2, and Qn, right? So Q1 star Q1, siya yung length squared ni Q1. Q2 star Q2, siya yung square ng length ni Q2, and so on. So that tells us na hindi lang orthogonal yung mga QIs to each other, but they all have unit length. So that means Q1, Q2, until Qn are all actually they form an orthonormal set. Kasi lahat ng vectors doon ay normal in the sense that they have length equal to 1. They're orthogonal to each other, so they form an orthonormal set. Okay. Now here, I guess I introduce the Kronecker delta symbol. So hindi ko naman siya gaano ginamit, pero as a shorthand, delta ij, that means that's the symbol telling us that 1 must be equal to, it will be equal to 1 if and only if the subscripts are equal to each other, and it will be 0 otherwise. Okay, and then I guess the explanation about the norms are self-explanatory. Ang kailangan ko lang for module 6 ay yung L2 norm. But probably I also need to look at yung L2 norm ng matrix. Oops. Hold on. Yeah, hold on. I think I have the wrong copy of the module. Okay, perhaps this is the last thing I'll need from module 5. And this is about matrix norms. Though in module 6, if you have started browsing it, I always rely on MATLAB to compute the matrix norms for me there. But anyway, just a quick recap about this. So we define the norm of a matrix this way. So it is the supremum of the norm of AX. So this subscript here will just tell us to refer to the norm defined on CM. Right? Kasi itong AX, if your matrix A is m by n and X is an n by 1 vector, so AX is m by 1. So if I want to measure the length of the vector AX, that should be with respect to the norm we define on CM. And then X is an n by 1 vector. So I am measuring it with respect to the norm I defined on the vector space Cn. All right. And then I take the ratio, the supremum ratio. By the way, the supremum is just the generalization for the maximum. Okay. Yung maximum kasi ginagamit lang natin usually if you are finding the maximum within a finite set. Pero pag yung set naging infinite na o naging hindi na discrete, hindi na natin ginagamit yung term na maximum, but instead we're using the term supremum. All right. So we are taking the supremum of the ratio between the length of the image under A of any n by 1 vector, which turned out to be an m by 1 vector, over the length of the pre-image X. So basically, we are just looking what is the maximum ratio that the matrix A can extend or can stretch or condense a vector X. So pwede nyo tingnan yung matrix A to be something that transforms a vector x. Okay? So yung result ng transformation na yon ay si ax. And then you compare the length of the vector ax and the vector x. The maximum ratio is what we call the norm of the matrix. So the measure of a matrix is by how much can it stretch a vector after the imaging or the transformation process. So ito yung norm ng matrix A, siya yung pinakamalaking factor by how much we stretch x into a vector ax. Okay. So and then norms on matrices can be induced by norms on vector spaces. So for instance, we have the L1 norm for a matrix. The L1 norm for a matrix, again, by definition, this is just the supremum of the L1 norm of AX all over the L1 norm of X. Okay? So kukunin nyo lang ang lahat ng possible ratio, and then you take the supremum. Of course, doing this by hand is almost impossible to do it by a brute force, because there are infinitely many vectors X in Cn or in Fn. So it's impossible to take the supremum by hand. But thanks for some deductive processes or deductive derivation, it was shown that this supremum is just equal to this guy, which is just the maximum absolute column sum of A. So I hope you had some exercise doing it. I would have suggested that you do these calculations by hand, but of course, if you're more comfortable doing it with MATLAB, then that's fine. It's just a single line of command. But it's a good exercise to find the L1 norm by hand. So to the sum of the, and then take the maximum column sum, and that's going to be the one norm. The infinity norm, by definition, is supposed to supremum ratios between the infinity norm of AX and the infinity norm of X. But again, by brute force, it's impossible to do. Thanks for some mathematician who did some deductive derivation. They found out that the infinity norm for a matrix is nothing more but the maximum absolute row sum of A. So what you need to do, take the sum of the absolute value of all of entries in a row, and then you pick which is the row with the highest absolute sum, and that's going to be the infinity norm. Okay. Medyo mahirap lang i-compute by hand yung L2 norm ng isang matrix, but this is what we'll be more interested in when we jump to module 6 in a while. But again, by definition, this is the supremum between the L2 norm of AX and the L2 norm of X. But it turns out that the expression did not simplify as nicely as what happened to the L1 and the L infinity norm. It requires computing the maximum singular value of A. And that's what you have here. Sigma sub max of A is the maximum singular value of A. I actually drafted module 6 with the first topic, singular value decomposition, but I don't think we will have enough time if we will cover that. So unfortunately, I have to drop that for module 6. So we will heavily rely on MATLAB in computing the L2 norm for a matrix. But luckily, the L2 norm for the matrix in MATLAB has a nice syntax. I guess it's just a norm of your matrix A. So as simple as that. So, or you can write it as norm A2. So you can also use this to specify the p-value. So the p-value is the LP norm that you used in the definition. Okay. So the first three examples tell us that if you have a vector norm, then it will automatically induce a matrix norm. You could define, you can actually define the L3 norm for a matrix. The L3 norm for a matrix is just the supremum of AX, or the L3 norm of AX all over the L3 norm of X all over all vectors in your space, all right? But unfortunately, I don't think this simplified nicely. Kaya kung makikita nyo, in any textbook, they only discuss three induced norms for matrices: the L1 norm, the L2 norm, and the L infinity norm. Kasi hindi ganun kasimple yung formula na madiderive if you want to compute the L3 norm for a matrix, all right? And even MATLAB only has intrinsic functions for computing the L1, L infinity, and L2 norm for a matrix. I don't think it has an L3 or an L4 or a built-in command for the L3 or L4 norm of a matrix. So yun lang tatlo, plus the Frobenius norm here. So I just included the Frobenius norm just to illustrate that not all matrix norms are induced. Kasi sabi natin just here that if you have a vector norm, then it will always induce a corresponding matrix norm. Kunin mo lang yung ratio ng vector norm ng mga vector norms, right? Pero hindi lahat ng norms sa matrices ay defined in that way. For instance, you have the Frobenius norm, which is simple enough to compute. We denote it by norm sub f, right? This is just the square root of the trace of A of adjoint times the matrix A. So computin nyo lang yung adjoint ni A, multiply sa A, then take the sum of all the diagonal entries, take the square root, then you get the Frobenius norm. The Frobenius norm usually is what we use as a replacement for the L2 norm because of some of its properties and the nice way of how it is computed. But yeah, I just included it here just to illustrate that not all matrix norms are induced by vector norms. All right. Okay, and I think I have all what I need for module 6. Do you guys have any questions? All right, if none, then let me open module 6. Did you guys had the chance to look at it now? Or hindi pa? I think I uploaded it around 12 midnight or close to midnight yesterday. So yeah, I didn't bother announcing it to the group because yeah, I remember I need to apologize. I didn't realize that sometimes my emails in the wee hours of the nights or the feedbacks to the homeworks, the email notifications are causing some anxiety among you. So I sincerely apologize for that. That's why I tried as much as possible to limit the number of announcements in the last week. And also, I'll try my best to grade homeworks during normal hours, not in the wee hours of the day. But since I expect that submissions will start to flood, so if you get anxious or if you don't want to get notifications in the wee hours of the morning, so please let me know so that I can untick the notification button when the notification when I'm grading your work para hindi kayo mo-notify right away if you don't want to get notified about it. Or another thing is that you can just mute your email probably during the wee hours. So that's for you to avoid getting those notifications. Because I cannot promise right now to finish grading during the normal hours of the day kasi medyo because I expect na dadami yung submission. So I need to work overtime just to have everything graded before the deadline for grades. So yeah. So, and again, I apologize if those lots of notifications and notifications in the wee hours are causing you anxiety. So yeah. All right, so let's move on. So module 6 is entitled Some Important Processes or Algorithms in Linear Algebra. But unfortunately, when I was writing it, I was just able to include one, or actually, based on how you will count, 1, 2, or 3. And I guess that would be more than enough for the coming week. Ayoko na, but hopefully here I can illustrate some of the processes that we do in linear algebra. This anyway, with some algorithm. So this will just be a quick survey and a quick illustration of these processes. Sorry. Okay, so I hope, yeah, sorry kung nagchachoppy uli. I hope this will become better. So yeah, let's see. The first process here is the Gram-Schmidt orthogonalization process. I cannot imagine teaching linear algebra without at least the Gram-Schmidt orthogonalization process. The Gram-Schmidt orthogonalization process takes in a linearly independent set and then turns it into an orthogonal set. We have said earlier by a theorem that that all orthogonal sets are linearly independent, but not all linearly independent sets are orthogonal. So the Gram-Schmidt orthogonalization process is a nice way on how to convert your linearly independent set into an orthogonal set. And this is important because I've mentioned earlier that most nice bases or stable bases for vector spaces are the orthogonal ones or the orthonormal ones. So kaya nagiging importante yung Gram-Schmidt. Because if you have a basis, which is fine as an input to the Gram-Schmidt process, kasi linearly independent naman siya. So pag binigay mo siya sa Gram-Schmidt, yung result mo ay orthogonal na. And the nice thing about this process is that it preserves the span of your set. So ibig sabihin kung basis yung ipapasok mo sa process, yung makukuha mo ay isang basis pa rin. But not just the basis, but it's gonna be an orthonormal basis. Okay? And then we'll also discover one nice application of the Gram-Schmidt process later on. So I wrote all those nice things about the Gram-Schmidt process, but there are two versions, at least two versions of the Gram-Schmidt process. You have the classical version, which is usually the one used in teaching the process to students, especially if you will be doing things by hand. So it's nice because it's a straightforward calculation, though the modified Gram-Schmidt process is also easy to follow by hand. But the classical version gives the formula in a nice way that you can use these in the theoretical analysis. So kung may prove kayo about Gram-Schmidt process, kadalasan ang ginagamit ay yung form na nanggagaling dun sa classical version. But the modified version is more useful in practical purposes. Wherein kapag kailangan mo talagang mag-compute ng malalaking vectors or malalaking matrices, we go the modified version because you will see later that the result of the numerical implementation of the classical version of the Gram-Schmidt process is not that stable. But I will remark earlier that it doesn't matter theoretically whether you use the classical or the modified version, you should end up with the same orthogonal set. Pero pag ginawa mo na yung computations inside a computer, things can go haywire. So yun yung kagandahan ng modified version. Okay. But let's look at the classical Gram-Schmidt process first, and that's what you can see in algorithm 1. I hope medyo nag-stabilize na yung signal ko. So, yeah, but sorry, I cannot do anything about that. Dalawa na nga yung providers ko ngayon. So baka yun yung dahilan minsan ba't nag-choppy. My laptop is shifting from one internet connection to another. But yeah. But let's go to algorithm 1. This is the classical Gram-Schmidt process. So again, the input is a linearly independent set of vectors coming from Fn. So yung mga vectors na yun, tawagin natin A1, A2, and AN. And then what you get as an output from algorithm 1 is an orthonormal set, Q1, Q2, and Qn. So it's an orthonormal set, so that means that Q1 is orthogonal, or elements of this set are orthogonal to each other, and that the length of each of the QJs is equal to 1. Okay? And let's see how the process go. Though hindi ko alam kung paano maganda siya i-discuss kasi formula-based lang naman talaga siya. So the first step is set Q1 to be equal to the normalized version of A1. So yung unang papasok dun sa orthonormal set would be a normalized version of A1. So si A1, yung length niya, gawin mo lang, i-divide mo lang siya by its length so that the resulting vector Q1 will be of length 1. So papasok siya ngayon dun sa orthonormal set. And then what we will do in the successive steps is to get A2 and subject it to a process with the existing QI. So kukuha ko ng vector dito. On my jth step, I'll get AJ coming from the original set. And then I will transform it to QJ. But how do I translate it to QJ? It will undergo a process that will require all previous orthonormalized elements of your set already. So in particular, kung nasa jth step ka na, step number J, so kukunin mo si AJ coming from your original input set. Okay? And then, siya yung magiging basihan, how do we get QJ? Pero in computing QJ, you need to take the inner product of AJ with all existing QIs. Kasi meron ka ng Q1, Q2 until Q sub J minus 1 dito sa set na yon. So na-compute mo na hanggang Q sub J minus 1. I-inner product mo si AJ sa lahat ng mga yon. And then multiply mo kay Q1 yung inner product nila. Take the sum, subtract it from AJ, you'll get your unnormalized QJ. And since we promised an orthonormal set in return for your AIs, all right? So yung makukuha nating vector na to, i-divide lang natin by its length. And that's what your QJ would be. All right? So again, this is entirely mechanical, computational in nature. So probably it's best not to dwell in the formula itself, but let's look at the formula in action. So let's look at example 61. This set B is starting to become our favorite basis for R3. So 1, 0, 0, 1, 1, 0, 1, 1, 1. Let's try to orthonormalize it, right? So again, we have noted na hindi siya orthogonal. Because if you take the the inner product of these two vectors, you get something not equal to 0. And then if you take the length of 1, 1, 0, it's square root of 2. So hindi siya even normalized. Okay? So let's subject it to the classical Gram-Schmidt process. So step number 1, deal about Q1. What will Q1 be? It's going to be the normalized version of A1. So si A1 ay 1, 0, 0. I-normalize lang natin siya by dividing it by its own length. But it's already of length 1, so Q1 will be 1, 0, 0. Okay? Off to a good start. Kasi mukhang napakasimple na nung Q1 to begin with. All right? And then Q2. How do we compute Q2? Again, for Q2, may typo. So, sorry, may typo siya kagad. this should be A2 and A2. Right. Okay. So ang gagawin natin, kunin mo si A2, ida-dot product mo siya dun sa mga existing QIs na. And then i-multiply mo siya dun sa existing QI, then isusubtract mo mula kay A2. So copyahin nyo kagad si A2 there, okay? Minus dot product ni Q1, siya palang luckily yung existing Q, and the A2. And then the result is a scalar, so multiply it by Q1 so that we get a vector. Okay? And then we divide this vector by its length para maging normalize siya. All right? So let's expand what these quantities are. So A2 is 1, 1, 0. Q1, we know is already the elementary vector E1. A2 is 1, 1, 0. And then this is Q1. And then the denominator here is just the length of the numerator. Okay? Then let's compute the inner product. So inner product, kunin niyo yung conjugate transpose nito. Pero in theory, what happens is that we take the conjugate, then multiply mo lang siya component-wise, then take the sum. Luckily, ang binigay ko lang dito ay real number. Hindi na ako pumunta sa complex. So hindi ko na kailangan i-conjugate. So 1 times 1 plus 0 times 1 plus 0 times 0. That gives me 1. That tells me that 1, 0, 0 and 1, 1, 1 pala is orthogonal. Hindi pala siya orthogonal to each other, sorry. But yeah, the inner product is equal to 1 times Q1. Q1 is 1, 0, 0. Okay? So, and then we subtract whatever we get from A2. So we get 0, 1, 0. And we were supposed to normalize it. So we divide it by its length. But its length is just itself. Its length is equal to 1. Because this is 0, 1, 0 I unit vector now, or normal vector now. And true enough, this is actually E2, right? So 0, 1, 0. So ito yung magiging Q2, the second element of our orthonormal basis. All right. Now let's jump to the third step. So third step, at this point, at the third step, we already have two Qs, right? Meron na tayong Q1 and Q2. Kaya yung numerator ay lumalaki na. Kasi nag-introduce na ako ng dagdag na elements. Okay? So here, I copy A3. That will be the minuend here. Tapos yung mga subtrahend, o yung mga thing after the minus sign, will be obtained by taking the cross product, the inner product of existing QIs. So meron akong Q1 at meron akong Q2. So kukunin ko yung inner product sa kanila ni A3. So when I take the inner product, I get two scalars. To get the vector, I multiply the inner product with Q1 and Q2 respectively. So dalawa na yung nasa subtrahend dito. Kasi dalawa na yung existing na QIs. So kasi kailangan ensure na si A3 ay orthogonal kay Q1 at saka kay Q2. It turns out that this subtraction and this subtraction is enough to guarantee that what I get after the subtraction is orthogonal to both Q1 and Q2. All right? And of course, you have the length, the normalization here. So kaya may length ka dun sa denominator. And then plug in those vectors. We get this. Straightforward calculation. So iba na to dun sa previous na ginamit natin for Q2 kasi ang pinapang dot product ko na dito ay A3. But their product is just equal to 1. And then copy 1, 1, 0. Compute the dot product here. You'll still get 1. And then copy this vector up there. And then perform the subtraction. You'll get 0, 0, 1. Of course, divided by its length. But you can forgo that because we already know that 0, 0, 1 is a unit vector, right? So normal vector siya kasi 1 yung length niya. And it turns out that Q3 will exactly be E3, 0, 0, 1. Okay? So it turns out that you have our basis B after the Gram-Schmidt process will just reduce to the elementary basis 100,010,001. Yes, Miss Al.
Sir, sorry, but can you show how to get the length? I'm kind of lost. Sorry lang po. Yung ginamit
Alin po?
to get the length of, let's say, of a 001.
Oh, sure, yeah.
Thank you, sir.
Yeah, this is the Euclidean length. So if you have a vector x, this is just the square root of x1 squared plus x2 squared plus x3 squared. So if you have 001, so that's the square root of 0 squared plus 0 squared plus 1 squared. So the usual Euclidean length.
Okay, thank you, sir.
Yep. Yeah. So that's why maganda na mag-stick tayo sa L2 length kasi siya yung pinaka-natural para sa atin, right? So that's length 1, so that's fine. We get the elementary matrix, the elementary basis back. Okay. Now, let's try another example. This time, lagyan na natin ng ibang numbers para maging mas interesting. Another basis for R3 is this matrix, this set A, 1, -1, 1, 1, 0, 1, 1, 1, 2. You can check it's a basis, so linearly independent sila, and they span R3. But obviously, hindi siya orthogonal. Kasi if we take, say, the inner product of this guy and this guy, so what will we have? We'll have 1 times 1, so that's 1. And then multiply the second components, -1 times 0, we get 0. And then multiply the third components, 1 times 1, we get 1. So the inner product of the first two vectors is equal to 2, not equal to 0. So obviously, hindi sila orthogonal. But I claimed here that it is a basis, so believe me that they are indeed indeed form a basis. So linearly independent yung mga yan. So pwede ko silang i-undergo or i-subject sa Gram-Schmidt process. Okay. So let's take A1 to be 1, -1, 1, A2 to be 1, 0, 1, and A3 to be 1, 1, 2. Then let's go classical Gram-Schmidt. So classical Gram-Schmidt, step 1, kunin mo si A1. I-normalize mo lang siya. Siya yung unang Q mo. So A1, copy that over, and then compute the length of A1. So the length of A1, again, is 1 squared plus -1 squared plus 1 squared. So that will just be square root of 3. That's how we got the length there. And so Q1 will be this guy, the vector containing 1 over root 3, -1 over root 3, and 1 over root 3. Tapos, hindi na to masayang gawin mano-mano kasi ang dami ng square roots. This is one thing you can do. If I ask you to do something by hand in the homework, tapos may mga pangit na numbers na yan dyan, you can use calculators para gawin yung intermediate steps. What I meant by hand is not to ask MATLAB to do everything for you, okay? And then it would be nice if you have a calculator or if you have a solver that can give you exact values. I mean, if you have square root of 3, hindi niya ibibigay yung 1 point something para ma-preserve nyo yung pagiging exact ng solution. Kasi once you replace it by 1 point something up to some decimal digits, you won't get exact answers anymore. And you will see later that rounding off might cause us to get inaccurate results, especially whenever doing the classical Gram-Schmidt process. Kasi this is a highly unstable algorithm. So unless you do the calculations exactly, all intermediate calculations exactly, then you won't have any problem. But as early as you do truncation or rounding off, medyo magkakaproblema ka na. So it would be nice if your calculators can retain the square root of 3 in this quotient. So you retain it to 1 over square root of 3 as much as possible instead of replacing 1 over square root of 3 by its decimal approximation. Right? Yes, Miss I. Yeah, Miss, I have a question.
Sorry, I wasn't able to turn off on my mic. Sir, yung clarification lang po on the notation. Yung the A sub I is po are vectors, not po coordinate basis. Ano po?
Yeah. Yung mga AIs, yung A1, A2, A3, notation lang sila kung pang ilan siya dun sa set. So, hindi siya yung component.
Kasi we're using parentheses po instead of bracket.
Yeah. Though at this point, we don't have any distinction na naman between vectors and coordinates, right? But again, yeah, I kept the parentheses kasi ang ginagawa lang naman natin so far ay matrix times vector. And our interpretation here is that meron akong matrix times coordinates. So that's why I stick to using parentheses. But yeah, it's not a big deal. You can use vectors if you can use brackets if you want. That's perfectly fine.
Okay, sir. Thank you po.
Yep. All right. Now here's where the nightmare will start. Start computing Q2 by hand. So copy A2. Luckily, isa pa lang yung Q na meron tayo. So isang inner product pa lang yung pwede kong ma-form with A2. And that's Q1 inner product with A2. And then this is a scalar. Para maging vector, i-multiply ko siya by Q1. And this guarantees that what I get is orthogonal to Q1. Siya yung nag-guarantee ng pagiging orthogonal kay Q1. And again, I need to normalize kasi ang promise ay orthonormal vector, orthonormal set yung magiging output. Okay? So plug in the vectors in 1, 0, 1, that's our A2. And then Q1 dot product with A2 times Q1. And then we compute the dot product. So this guy, 1 over root 3. Luckily, this becomes 0. Then this is another 1 over root 3. So we take the sum. So we'll get 2 over root 3 as the inner product. So if you want to redo this by hand to double check, yeah, that's how we got that. Then times Q1, all right? And then we multiply all of the components here by 2 over root 3. So we get 2/3, negative 2/3, and 2/3 there. And we need to subtract it from 1, 0, 1. Okay? Then we'll do the normalization later. Medyo mahaba yung notation dito. You can devise your own ways on how to write it in a more compact way. Kasi I just wrote it this way kasi gusto kong maintain yung equality with Q2. Pag sinabi kong Q2 equals this guy, kailangan kong isulat yung denominator over and over again. Pero if you don't want to write the denominator over and over again, you can introduce, say, a Q2 tilde, perhaps, and then say this is the unnormalized version of Q2. So para numerator lang yung gagalawin nyo every time. And then para makuha si Q2, i-divide nyo lang si Q2 tilde by the magnitude of itself. Okay. Para makuha yung Q2, right? So you can be creative so that you don't have to write as long as a solution as what I have in here. Okay. So, okay, there we go. May fractions pa rin. Even mathematicians hate fractions, so kaya hindi masaya yung naging computation dito by hand. Hopefully, I didn't miss anything, though I check it with my MATLAB code, so mukhang tama naman siya. Okay. So 1, 0, 0 minus this guy will give me this. 1/3, 2/3, and 1/3. But I need to normalize, so I need to take to compute the norm. Like again, the norm is just the square root of the squares of the component, and then taking the sum. So 1/3 squared is 1/9. Second component is 2/3, so 2/3 squared is 4 over 9, plus 1/3 squared is 1/9, so that's going to be root of 6/9. That's how I got that, right? And then it's in the denominator, so magiging 3 over root 6 siya. When I turn the division into a multiplication, I have this matrix from this vector on top, and then and then I'll need to multiply them component-wise with 3 over root 6. And this is what I get as my second vector Q2. Alright? At lalong hindi masaya yung Q3. Kasi yung Q3, magiging ganito na siya. In computing Q3, we already have two Qs. Meron ka ng Q1 and Q2. That means meron ka ng dalawang isusubtract mula kay A3. What are those subtrahends? Take the dot product of A3 with the existing QIs. They will give you scalars. To get back your vector, multiply this inner product with Q1 and this inner product with Q2. Tapos napagod na yata ako dito to write everything properly or everything in detail. So tinanggal ko na yung denominator and I said I'm gonna normalize later na lang. So here I computed Q1, the inner product of Q1 A3 times Q1. Isa-isa ko na lang sila. Okay. Plug the vectors in. And then the inner product, again, take component-wise product, then sum them up. So multiply mo lang yung mga yan. Take the sum, that's going to be your inner product. It's 2 over root 3. Multiply that to your vector, scalar multiplication. It will give us this guy, 2/3, negative 2/3, and 2/3. Do the same thing for the second subtrahend. And then we'll get this guy, 5/6, 5/3, and 5/6. And so the unnormalized Q3 is computed by A3 minus the two vectors that we computed before. So just copy them over, perform the subtraction, we'll get negative 1/2, 0, 1/2. Okay? Then compute the L2 norm. L2 norm is the square root of 1/4 plus 1/4. So that's going to be square root of 1/2 as claimed here. And then all we need to do is to divide this guy by this length. And if you do so, you'll get Q3 to be equal to this guy. Okay? So the result of our Gram-Schmidt process is this orthonormal set. And in most instances, this is a nicer basis than the set A that we have at the onset of this example, especially for numerical purposes. Kaya mahalaga yung paggawa ng yung Gram-Schmidt process or the orthogonalization process. And also, there are certain situations that you will need an orthonormal set. So the easiest way is to use the Gram-Schmidt process. Any question or comment aside from the possible complication of the process? Because I hope you can imagine if you have, say, if you have 5 vectors coming from Cn, coming from C5. So, I mean, or R5. So meron kang mga 5 vectors. So 5 sila. So imagine the process, how messy the process would be pag pumunta ka na sa pag-compute ng Q3, Q4, and Q5. Okay? But I hope the process makes sense. Wala naman tayong exam, so wala kayong sasauluhing formula. You can have the algorithm in front of you whenever doing the calculations. So, yeah. And then just a theoretical result here. The nice thing about the Gram-Schmidt process is that it doesn't only orthogonalize, or it doesn't just make your linearly independent vectors to be orthogonal to each other, but it preserves their span. So ibig sabihin, whatever is the subspace generated by your starting set A, remember A should be a linearly independent set, then that subspace is equal to the subspace generated by the orthonormal set resulting from the Gram-Schmidt process. So wala kang nakakalimutang elements mula sa span ni A papunta sa span ni O. So that means if you start with a basis, you'll end up with another basis. If you end up with, if you start with a set spanning, say, a subspace W, then the orthonormal basis, the orthonormal set that you get will also span the subspace W. So walang nawawalang information insofar as being a vector space is concerned kapag ka ginawa yung Gram-Schmidt process. And that's amazing because parang napakasimple ng ginagawa natin in the Gram-Schmidt process. You started your non-orthonormal vector, magsusubtract ka lang ng something that has to do with the inner product, and then all of a sudden after the process, you'll end up with an orthonormal set. And that orthonormal set contains all the information that the original set also carries. So, yeah. I went away with the proofs this time for module 6 because the purpose of module 6 is to give you a hands-on experience with at least some of the algorithms for in linear algebra. So kaya I didn't include the proof, and I won't ask you about the proof of theorem 42. And again, the utility of theorem 42 is on the result itself rather than the proof. Okay. Okay, so remark 7 is also a nice thing. It assumes you have n vectors coming from Cn, okay, and that the QIs are orthonormal. So kung orthonormal sila, ibig sabihin yung matrix Q formed by the columns, formed by taking the QIs as the columns, is unitary. Okay, and then let's quickly see why. Though I said it's a proof, pero computational naman siya, so exemption siya dun sa rule. So to prove that, remember to prove that a matrix Q is unitary, dapat meron kang Q star, dapat ay equals Q inverse. Or Q adjoint times Q should be the identity, right? That's the definition of being unitary. So if I want to show that this matrix Q is unitary, I need to show that Q star Q is equal to the identity. All right? And how can I show that? Well, I'll just need to compute Q star Q explicitly. So si Q, sabi natin, siya yung matrix whose columns are the vectors Q1 until Qn. So just copy that over here. There you go. And then Q adjoint, or the adjoint of Q or Q star, is simply the complex conjugate transpose of Q. So yung mga rows, sila ngayon ay magiging columns. Baliktad. Yung mga columns, sila yung magiging rows. Pero dahil adjoint yan, kailangan kunin yung conjugate transpose ng bawat column. All right? And then if I do the matrix multiplication, this matrix times this matrix. So remember, this is n by n. This is n by n. So the result is another n by n matrix. By the way, this notation is the aij notation as before. Okay. So ang nasa ij entry ng kanilang product ay qi star qj. Okay, kasi kukunin ko yung row dito, multiply ko nung column dito, that will be the ijth entry, right? Take the entry in the ith row here, which is qi star, and then the jth column here, which is qj, that will be our entry on the ith row and jth column. All right? But what is this quantity? Remember that our assumption is that the QJs form an orthonormal set. And we have noted that if you have an orthonormal set, QI star QJ will just be the Kronecker symbol, right? Because this will be equal to 1 if I is equal to J. Kasi magkakaroon ka lang ng QI star QI, which is basically the length squared, right? The L2 norm squared. Pero sabi natin, orthonormal yung mga QIs. So, ibig sabihin, the length of QI is equal to 1. So, that means QI star QJ will be equal to 1 when I is equal to J. And then by orthogonality, when I is not equal to J, then the result will be 0. Okay? So that means yung entry ng Q star Q ay equal kay 1 kapag ka si I ay equal kay J. So ibig sabihin, yun lang yung diagonal entries. 1, 1, 1, 1, 1, 1, 1, and so on. Kasi sila lang yung I equals J. Tapos 0 na siya kapag ka si I ay not equal to J. So 0 siya dito, 0 siya dito. But what is that? That is exactly the identity matrix. Okay? So in order to complete the proof, do the same thing but compute Q star, and you'll be able to show that this is also the identity matrix, proving that Q is a unitary matrix. All right. Okay. Now, I said that algorithm 1 is very simple and it has its theoretical value because most statements involving the Gram-Schmidt process are proven using the formulas you see in algorithm 1. But once you go into a computer and then try to calculate the orthonormal set coming from your linearly independent set and you use the classical Gram-Schmidt process of algorithm 1, then the results are not reliable for all cases because the classical Gram-Schmidt process was performed in such a way that the operations are, or the arithmetic operations there, are arranged in a not so good way. So nagiging unstable siya. So as a remedy, we use the modified Gram-Schmidt process. So just to be clear, algorithm 1 and algorithm 2 are equivalent to each other. So it doesn't matter if you do algorithm 1 or algorithm 2 by hand and you deal with exact numbers, then their results must be equal to each other. Parehas sila ng ibibigay sa inyo. However, once you go into a computer wherein the computer is a finite machine, after every operation, the computer will round off the number and store it in its memory. So yung gagamitin mo to the next step is already rounded off. So magpapatong-patong yung round off error. So kasi sa paggawa ka sa computer ng series of operations, gagawin niya yung first operation, but the result will be already rounded off depending on what your hardware is or what the software is designed to do. So rounded off na siya. Tapos yung result na yon, siya yung gagamitin sa susunod na arithmetic calculation. So meron ka ng rounded off errors, yun yung gagamitin mo sa susunod na calculation. So imagine the round off errors will propagate. And that's what happens with algorithm 1. There are lots of operations, they're arranged in a not so good way, so nangyayari, nagpa-pile up yung round off errors. And to remedy that, we have the modified Gram-Schmidt process. And again, this is equivalent to algo 1. So if you have a perfect machine, they will give you the same answers. But if you're performing things in a computer with a not so good machine epsilon or machine precision, then posibleng magkaiba na yung ibibigay sa'yo ng algorithm 1 and algorithm 2. All right? So let's see how it goes. The thing about the modified Gram-Schmidt process is hindi to iterative, hindi siya nagiging build up on existing QJs. So you'll see here that what it does is this. So tatawagin ko lang yung mga inputs, AIs, by another name, call it VJs, assign them to the vector VJs, right? Para lang, kailangan ko lang siya para maging klaro yung nangyayari dun sa algorithm. Okay? And then now I start from J from 1 until N. Okay? So at J equals 1, I will take V1 over the norm of V1, normalizing. Basically, normalization process lang. Okay? So that would be on the J step. However, I will not end there, but I will update the VKs. Yung mga hindi ko pa nagagamit na K, because K will go from J plus 1 until N. So on your J step, si QJ pwede mo nang i-compute. Ino-normalize mo lang yung VJ. Alright? But before you leave the iteration, before you leave iteration j, you need to update the v case where k goes from j plus 1 until n. So yung v sub j plus 1, v sub j plus 2, until vn kailangan mong i-update. And you update them using this formula. Tapos pagpunta mo kay step j plus 1, yung qj mo na ay magiging vj plus 1 over the norm. Pero this vj, norm of vj plus 1 yon. Pero yung vj plus 1 na ginamit mo sa step na yon is updated. Hindi na siya yung original na vj, right? It is updated from the previous step. Okay, probably it's easier to make sense of what is going on by looking at an example. Okay. Easy example ulit, example 63. So we returned back to our favorite basis B for R3. Okay. Step 1, tawagin mo yun silang mga VIs. So V1 I see A1, V2 is A2, V3 is A3. Okay, that's our initial V1, V2, and V3. But again, we will be updating the VIs later. Okay. So step 1, J equals 1. J equals 1 na ako. So ang Q1 ay normalized version ni V1. So si V1 ay ito, normalize ko lang siya. That would be my Q1. But after computing Q1, I need to update V2 and V3. Ina-update ko yung VJ plus 1 at VJ plus 2. So in this case, dalawa lang naman yung kailangan kong i-update. So si V2 at si V3 kailangan kong i-update. I don't need to update V1 anymore because I already have Q1. And for that, I already used V1. So I can forget about V1. Ang i-update ko na lang ay si V2 and V3. And how do you update V2 and V3? Well, you update them according to this formula. Okay? So sarili niya minus inner product with the Qj that you have just computed, and then the Vj that you want to update times the just computed Qj. So in this case, na-compute lang naman natin ay si Q1. So kukunin ko si yung lumang V2 minus inner product nung kakocompute lang natin na Q, so which is Q1 times lumang V2. Then whatever the inner product is, I'll multiply it with yung kakocompute ko lang na Qj na Q value, which is Q1. Okay? So V2 old, inner product of Q1 and V2 old times Q1. And then that thing will be our new V2. And then I'll also update V3. How do I update V3? Old V3, minus inner product nung Q na kakakompute ko lang, and then the old V3 times yung kakocompute lang na Q. All right? Do the calculation, you'll get 0, 1, 1. So they would be the new V2 and V3 that we will use in the next iteration. All right? Now we are at J equals 2 na. So at J equals 2, normalized V2, that will be our Q2. So as a V2, the updated V2 is 0, 1, 0. Normalized na siya. So siya na si Q2. At dahil na-compute ko na si Q2, I can forget about V2 as well. Kailangan ko na lang i-update si V3. Okay? How do I update V3? Old V3 minus inner product. Inner product of who? Inner product nung kakocompute mo lang na Q, which is Q2, versus the old V3. You get a scalar. To get a vector, multiply that scalar with yung kakocompute mo lang na Q2. All right? And that would be our new V3. Carry on with the calculation of this guy. You're going to get 0, 0, 1 as V3. And then iteration 3, here we have J equals 3. So Q3 will be just the normalized version of V3. And then I have used up all of the VJs, so nothing more to update. And that tells us we're done. And just collect the Qs. They will be the orthonormal set. 2 and off, we get 1, 0, 0, 0, 1, 0, and 0, 0, 1, the elementary basis, which is the same as what we got using algorithm 1, the classical Gram-Schmidt process. All right? Okay lang ba? Are you getting the feel of the algorithm? So kung hindi clear, kung binasa nyo lang yung algorithm, I hope this discussion helps, and you can retrace back the steps in the examples para ma-perform nyo yung modified Gram-Schmidt. Okay? Maybe if you want, we can also talk about example 64, which considers the set A that we considered earlier. Okay? Pero papahapiawan ko na lang yung discussion. Medyo nagreklamo na naman yung lalamunan ko. All right, let's see. Okay, first step, initialize the VJs. V1 is A1, V2 is A2, V3 is A3. Right? Iteration 1, J equals 1. Compute QI, which is Q1. Gagamitin ko lang, kailangan ko lang i-normalize si V1. Okay? And that gives us Q1. We computed Q1, so we ought to update V2 and V3. Again, how do we update V2? Old V2 minus just computed Q. Take its inner product with the one that with the old V2 times the just computed Q. Right? Plug all those vectors in, you get this guy. Perform the calculations, will give you the new V2. Okay, ito yung gagamitin ko sa susunod na step. Then I also need to update V3. Old V3, when I say old V3, that is the V3 coming from the previous iteration, minus the inner product of the Q that we just computed, and the old V3, multiply it to the vector Q1, which we just computed. Plug those values in, perform the arithmetic, you get 1/3, 5/3, and 4/3. So again, I hope that when I ask you to do calculations by hand, you do it something like this. Though you can use calculators in the intermediate step, but I hope you retain exact fractions, exact radicals, para walang maging loss of significant digits. Because that's one purpose why I want you to do the calculations by hand. Okay. Then carry on. Step 2, or iteration J equals 2. We can compute Q2 by just normalizing V2. And then after using V2, forget about V2. So we only have one vector left on our storage, and that is V3, which ought to be updated. Okay. Update V3 how? Old V3 minus the inner product of Q2, the just computed Q value, and the old V3, multiply it with the just computed Q value, or Q vector. Okay. Plug the things in. Perform the arithmetic. You get -1/2, 0, 1/2. And this would be the new V2 and V3 that will be passed on to the next iteration of the algorithm. Okay? Iteration 3. For iteration 3, we get this guy, okay? We just need to normalize V3. And then we don't have any V in our storage anymore because we already forgot about everything. Kakagamit lang natin ng V3, wala nang kailangang i-update. So this will be our Q3. So all that's left to be done is to collect your QIs into your set O. And note that this is also the same set O that I got from the classical Gram-Schmidt. All right. Any question? Can I see a thumbs up if the process makes sense, both the classical and the modified Gram-Schmidt? Okay. Kaya nyo na bang gawin siya by hand later? Parang pinagawa ko siya sa homework by hand. Pero syempre, hindi naman ako terorista na 5 by 1 yung ipapagawa ko sa inyo. No? Okay, I hope I illustrated how machine implementations can vary, or hindi pa. I don't think I did that. But here I started talking about how they will differ. Example 65, okay? So, but before talking about the applications of the classical and the modified Gram-Schmidt process, I had a few words about ill-conditioned matrices. We say a matrix is ill-conditioned if, technically, if it has a high condition number. Pero anong implication niya? If you have an ill-conditioned matrix, hindi siya magandang gamitin for numerical purposes. Or we don't want computers to touch ill-conditioned matrices because results become unreliable. Okay. But first, let's quantify what being ill-conditioned is. So a matrix is ill-conditioned based on how large its condition number is. The condition number of a matrix or an invertible matrix denoted by kappa of A sub P. I just use the subscript P here because there are lots of ways how to compute the condition number, but they all depends on matrix norms. So kung meron kang P norm for a matrix, you can define its LP norm condition number. So the LP norm condition number of a matrix, of an invertible matrix, is kappa of A sub P, which is just the product of the LP norm of the matrix and of its inverse. So kunin mo lang yung LP norm ng matrix A at LP norm ng A inverse, multiply them together, that would be the condition number. So if A is non-invertible, we say its kappa is positive infinity. If kappa is small, then A is said to be well-conditioned. And if kappa is large, then it is ill-conditioned. Okay? But how small is small? It depends from application to applications. Yes, Ma'am Rina?
Sir, sorry po, binabanggit niyo na po, itatanong ko po sana kung paano ma-measure yung pagiging small.
Pagiging small, yeah.
Diba?
Yun yung problema. Walang convention o walang agreement how small is small or how large is large for condition numbers. It usually depends on the kind of application. So ideally, we want kappa to be as close to 1 as possible. Pero yung pagiging close to 1 is also subjective because condition numbers can blow up to powers of tens. So kaya kung meron kang kappa to be 100, that might still be good for most applications, though malayo na siya kay 1. Pero technically, we can consider that to be still close to 1 kasi ang mga kalaban niya ang condition numbers ay mga 10 to the 26, 10 to the 34. So those are the ill-conditioned matrices. But if you still have, say, 25 as your kappa, that is still that in most cases is still considered to be well-conditioned. Pero just to give us an idea, paano mo ma-measure yung pagiging small or large ng kappa is with the loss of significant digits that you might encounter. So if, as a rule of thumb, if your kappa is 10 to the k, then we say that we can lose up to k decimal digits, up to k significant digits due to instability alone. And I say instability alone, wala pa dyan yung rounding off errors, wala pa dyan yung algorithm errors, siya pa lang yung intrinsic dun sa problem. So you cannot solve the problem perfectly if you have a large condition number, because the fact that you have a large condition number alone exposes you to losing k significant digits. So yeah, kung na-compute nyo na yung condition number 10 to the power k, look at the power, and the exponent of 10 will tell you how many significant digits will you be losing. Okay? So nagiging relative pa rin siya to the computer that you are using. So usually computers has a machine precision of 16 digits. So usually ang machine precision ay 10 to the minus 16. That tells us na kapag ka nakakita ka ng number dun sa computer mo, dun sa computer result mo na 10 to the minus 16, that is virtually zero from the point of view of your computer. Kasi ang ginagawa niya lang, nagra-round up siya on the 16th decimal digit. So that means if your condition number is 10 to the, say, 10 to the 20, for instance, so that's a humongous number. So you can safely say that you have here an ill-conditioned matrix. But the interpretation there is that you should be ready to lose 20 significant digits due to instability alone. And that is bad if you have a computer that has 16, that keeps 16 significant digits. Kasi hanggang 16 lang yung decimal digits na ini-store ng computer mo. Pero yung matrix mo exposes you to losing 20 significant digits. So hindi na talaga appropriate na gamitin mo yung computer mo dun sa para sa matrix na to. Pero if your matrix, say, is or has condition number 10 to the 5th, 10 to the 5th is a large number. It's far from 1. Pero when talking about a machine with machine precision 10 to the minus 16, again, 10 to the minus 16 machine precision tells us na nag-round off si machine to the 16 decimal digits. Pero kapag yung condition number mo lang ay 10 to the 5th, that means that in the matrix or in using the matrix, we can lose 5 decimal digits. So ibig sabihin, or up to 5 decimal digits. So ibig sabihin, yung pang-anim na decimal na digit after the decimal point will be disregarded by our computer when using the matrix. Then okay pa tayo kasi kung malulose man siya due to machine precision at due to instability, marirecover natin siya because our computer rounds off only on the 16th decimal digit. So kahit yung matrix natin, ang condition number niya ay 10 to the 5th, ibig sabihin lang nun, nagiging prone na ma-disregard yung 6, 7, 8, 9, 10, and so on decimal digits. Pero on a computer that works with 16 decimal digits, hindi mawawala yung 6 decimal digits right away. So ibig sabihin, nare-recover natin yung supposedly mawawala natin from the instability by using a very high precision machine, which is 10 to the minus 16. So by the way, MATLAB, I think the machine precision for most MATLAB machines is 10 to the minus 16. Pwede nyo pa siyang gawing 10 to the minus 64, but that might be an overkill. So whenever using MATLAB, we want our matrices to have condition number smaller than 10 to the 16th. So if your condition number is still 10 to the 10th, 10 to the 9th, that is still good as long as we will using MATLAB, which has machine precision 10 to the minus 16. So hindi pa tayo masyadong mag-worry. And note that 10 to the 10th is still still a huge number. Pero from a point of view of a computer with a machine precision of 10 to the minus 16, that's still good. Okay? So I hope that answers your question, Ma'am Rina, about how close is close. Relative pa rin siya. Usually relative siya with respect to the machine or the computer that you are using. Okay. All right. So just to illustrate instability, we consider Hilbert matrices. So Hilbert matrices are square matrices whose entries are this guy. The ith entry is, typo alert, dapat ion, 1 over I plus j minus 1. So kung ang ni equal kay 5, meron tayong 5 by 5 Hilbert matrix. Ito yung itsura niya. So look at this one. This is on the I equals 1 and j equals position. So following this formula, dapat yung denominator ay 1 plus 1 minus 1. So that's going to be 1. That's how we got the 1 here. And then this guy here is where? This is on the 4th row and 4th column. So I and j are both equal to 4. So the denominator should be 4 plus 4 minus 1. That's equal to 7. So that's how I got the 7 there. So that means this Hilbert matrix is, or this, yeah, this is the Hilbert, the 5 by 5 Hilbert matrix. Okay. Now in MATLAB, hindi ko pa yata nabanggit. MATLAB can compute the L2 condition number. So the syntax for that is cond of A. It will give you the condition number of the matrix A in MATLAB, right? And this is actually the L2 condition number. So it's the norm, the L2 norm of matrix A times the L2 norm of the inverse of A. Okay? Pero hindi nyo na kailangan sabihin kay MATLAB to compute this. Just tell MATLAB compute cond of A. It will give you the condition number. Okay? So if we ask MATLAB to calculate the L2 condition number, so that's kappa 2 of the Hilbert matrix here, it will give us 4.7661 times 10 to the 5th. So that means that we should be ready to lose up to 5 significant digits due to instability. So hindi ako gagamit ng calculator na meron lang 5 significant digits in computing anything with the Hilbert matrix, kasi the results will be unreliable. But if I will use MATLAB with 16 digits, 16 significant digits, then I might still try to work with the Hilbert matrix H, but with no promises. Again, still, theoretically, the results should still be reliable. Kasi MATLAB has 16 decimal digits, condition number is 10 to the 5th, so we will just lose 5. So we will retain 11 significant digits pa rin, insofar as the results are concerned. Pero of course, there are several other factors that can affect computer calculations. Kaya hindi siya ganun pa rin ka-reliable. But at least I have room to spare. I have 11 significant digits to spare with MATLAB with this Hilbert matrix, so that should be fine. Okay. So another nice syntax that I will use in the code that I will show you is I of n. I of n is how MATLAB calls the n by n identity matrix. So ito yung pagtawag sa n by n identity matrix. Okay. Now I hope you see the attachment to module 6, which is I think I have 3 MATLAB scripts there. EX65.m, EX66.m, and EX67.m. So tingnan lang natin kung ano yung ginagawa niya. Okay. All right, so line 2, kailangan nyo lang i-declare ano yung size ng matrix na gusto nyo gamitin. Okay. And then line 3, you need to define what matrix A you want to use. In this particular case, I want to use the n by n Hilbert matrix just to illustrate instability. Okay, so automatically compute na ni MATLAB yung Hilbert matrix for us. Hindi nyo kailangang i-encode siya by hand. Okay. Line 4 just computes the condition number of the matrix A and store it in the variable K. And then here I provided you the implementation of the Gram-Schmidt process, the classical Gram-Schmidt process. Yung GS, hindi siya built-in kay MATLAB. So kaya kung gusto nyo gamitin yung GS para sa classical Gram-Schmidt, kailangan i-attach nyo dun sa script, dun sa MATLAB script nyo, yung function na GS na dinefine ko. So you will see GS, the function GS defined here in lines 28 to 47. So whenever you want to call GS, halimbawa, meron kayong gagawin sa MATLAB, kailangan yung Gram-Schmidt process, hindi siya built-in kay MATLAB. So ang kailangan nyo gawin, i-copy-paste ito dun sa dulo ng MATLAB script nyo. Kung mapapansin nyo, marami akong pinagawa kay MATLAB. So ang main program niya lang ay ito. Lines 1 to 27. That's the main program. And then lahat ng hindi built-in na function, kailangan ko siyang i-copy-paste dun sa dulo ng code o dulo ng script. Kaya makikita nyo, nasa dulo lagi yan. Required na nasa dulo ay yung mga functions. Function na yan, function na yan. So kung sa homework, gusto nyo gumamit ng MATLAB, tapos gusto nyo gamitin itong Gram-Schmidt na to, kailangan nyo itong i-copy-paste sa dulo ng script na gagamitin nyo for the homework. Alright? Para magamit nyo siya within the script. So that will prevent MATLAB from complaining pag tinawag nyo na si GSA. Kasi pagka tinawag nyo si GS of A, kasi hindi siya built-in, magko-complain si MATLAB unless si GS ay nandito sa baba. Define niya siya sa baba. Alright? So, ano yung ibibigay ni GS of A? So, line 5, GSA will give us two matrices. It will give matrix QC and matrix RC. Yung matrix QC, siya yung matrix na ang columns yung result ng classical Gram-Schmidt. Okay? Yung RC, siya yung right upper triangular matrix na na-form by using yung scaling factors mula dun sa classical Gram-Schmidt. Pero I don't want you to worry about RC. Just accept RC there for now. Just remember na yung columns ni QC, sila yung result ng Gram-Schmidt process. Okay? Now, remark 7 promise that the columns of QC, if the columns of QC are results of the Gram-Schmidt process, then QC should be unitary, right? Yun yung sabi sa result sa remark 7. Kapag yung columns ng matrix mo ay nanggaling sa Gram-Schmidt process, meaning they are orthonormal, right? Actually, hindi necessarily galing sa Gram-Schmidt process. Pero kung ang column ng matrix mo ay orthonormal, then your matrix is unitary. Yun yung promise ng remark 7. But the Gram-Schmidt process, be it the classical or the modified one, always gives back as an orthonormal set, right? So si QC, sabi natin, ang columns niya ay yung result ng Gram-Schmidt process. So ibig sabihin, ang columns niya ay orthonormal. And by remark 7, dapat si QC ay unitary. At dahil unitary siya, yung product ng kanyang conjugate transpose o ng adjoint niya, dapat at times itself, dapat ay identity matrix. Tama? So, QC apostrophe, this gives me the MATLAB, if you ask MATLAB to compute this will give us the adjoint of QC, of matrix QC. Kasi yung apostrophe kay MATLAB, kinukuha niya yung complex conjugate transpose ng matrix, which is exactly the adjoint of the matrix. So dahil as promised by remark 7, QC must be unitary, yung adjoint ni QC should be its inverse. So QC adjoint times QC must be the identity matrix. Tama? And that would be the test for orthonormality here. I will compute this. I expect it to be the identity matrix, right? But I'm not sure, so I'm going to call it for now the test mat C matrix. So siya yung test matrix para sa classical Gram-Schmidt. Okay? Pero alam ko dapat close as possible yan sa identity matrix kasi si QC dapat ay unitary. Tama? Alright? So to see the effectiveness of the classical Gram-Schmidt process, I will compare test mat C from the identity matrix. So kukunin ko gaano kalayo si test mat C mula sa identity matrix. So what I'm gonna do here is to call the n by n identity matrix, so that's what the I of n is for, minus test mat C, our test matrix. Pag sinubtract ko sila, makukuha ko yung error matrix, right? And to have an idea how big the error is, I will compute the norm of that matrix. And I want this to be small because I want the identity minus the test matrix to be as close to 0 as possible. Kaya gusto ko yung norm or the residual, the classic residual, or the residual from the classic Gram-Schmidt to be as small as possible. All right? And that's how I can measure the effectiveness of the classical Gram-Schmidt process whenever using ill-conditioned matrices. Okay? And then gagawin ko lang yung exactly the same thing, but now for the result from the modified Gram-Schmidt process. Now in line 20, I have here a line that calls the modified Gram-Schmidt process. Again, MGS is not built-in into MATLAB. So kaya kailangan kong i-define yung MGS dito sa baba. So that's the function in lines 50 to 65. If you will be building up a code and you're gonna need MGS, you need to copy paste MGS at the end of your code, right? Of your script. So dapat laging nasa dulo yung mga internal functions. So yung MGS, dalawang matrices na naman yung ibibigay niya sa akin, si QM at si RM. Tinawag ko siyang QM kasi Q siya yung unitary matrix, M manggagaling sa modified Gram-Schmidt. Right? And again, as promised by remark 7, QM must be unitary, or at least because I'll be doing calculations in a computer, I want QM to be very close to a unitary matrix. So to check if indeed it's nearly a unitary matrix, I will compute the adjoint times QM and call it the test matrix for the modified Gram-Schmidt process test mat M. And I expect that test mat M should be as close as possible to the identity matrix. Kasi we want QM to be close to unitary. Okay? And to measure the effectiveness, I will compute the norm of the error matrix. The identity, which is the expected result, minus the actual result, take the norm, you will have a number to measure the effectiveness of the modified Gram-Schmidt process. Okay? So, clear ba yung intent nung MATLAB script? I hope it is. Kasi meron yata kayong ganitong gagawin sa homework. Okay, let's see what the results are. Okay. Okay, the condition number of yes, Miss Al.
Sir, will it be okay with you if you can show it to us using really the MATLAB?
Oh, sure. Yeah, no problem.
Thank you, sir.
Yeah, let me just go to my computer and yes. Sorry, medyo over 2 hours na tayo. No? Hindi na to healthy, pero tapusin ko lang to para pwede nyo masimulan yung ibang problem sa homework. So let me share my screen. Okay, sorry. Sorry, may echo. Sandali lang. Yan, I hope wala ng echo. Let me see. Okay. All right, so I hope you guys can see my MATLAB screen. Try ko rin siya dito. Yeah. Okay, let's see. So, ito yung dinisect natin na script, the MATLAB script. I just need to go to this folder. Okay. So I chose n equals 5. Then let's run it. Okay. You can either press F5 or press this run button over here. Okay. So here, okay, here's the command window. I hope okay yung size ng window ko. Pero let's see if I can make it bigger. Okay. So here we see kappa is 4.7661 times 10 to the 5th. Remember, kappa is the condition number, right? So that means we should be, if we will go by the result of the classical Gram-Schmidt process, we should be ready to experience loss of up to 5 significant digits. So, but that's not a big thing to worry with our with MATLAB, because MATLAB is a 16-digit precision machine. So that should still be fine for most applications. But again, there are other factors involved that might make the results unreliable for this unstable matrix. And then the residual classic is 2.831. So that means that the norm of the difference between the identity matrix and the test matrix we got from the classical Gram-Schmidt process is about 2.8313. And let's see why. Remember, yung test mat C, gusto natin close to identity siya, right? So let's see test mat C. Test mat C, there we go. So this is test mat C. Increase close to 0. So this tells us that there is a little bit of loss of the orthogonality test mat C, which is nowhere close to identity matrix. This tells us na may nawalan tayo ng significant digits, and then roundup errors might have propagated more. So hindi identity yung nakuha natin. All right. And then, however, if I look at the residual coming from the modified Gram-Schmidt process, it's 8.4925 times 10 to the minus 12, which tells us na malapit sa identity matrix yung nakuha ko by multiplying QM adjoint to QM, which tells us maganda yung nakuha nating orthonormal, nakuha nating result using the modified Gram-Schmidt process. Let's see test mat M, but we expect this to be very close to the identity matrix. And sure enough, you see na this is 1, this is 1, this is 1. The diagonals are all close to 1. And then you look at all the off-diagonal entries. The off-diagonal entries are all of order 10 to the minus 12 or minus 14, or even 10 to the minus 15. So they are essentially 0. So that means, yeah, mukhang talagang mas effective yung modified Gram-Schmidt process kaysa sa classical Gram-Schmidt process. Even if on theory or on paper, they should be the same. They should give us the same orthonormal vectors. But since computations for us, and MATLAB is a finite machine, so ibig sabihin, there had been loss of significant digits really when we did the machine implementation. Okay. And again, it was promised na dapat parehas yung makukuha nating orthonormal set, right? But if you look at QC, Ito yung QC. So yung columns ni QC, siya yung orthonormal set. So this one, the first column, this is our first supposedly orthonormal vector. Then this should be orthonormal. This should be orthonormal. This should be our fourth orthonormal vector, and so on, right? Then tingnan natin yung QM. Ito naman yung nakuha ko QM. Parehas ba sila? Okay, their first elements are exactly the same, which is understandable. They share the first step or in computing Q1. Pero yung Q2 nila, tingnan natin kung saan nag-iba. 4629, 4433, 4059. Parehas pa rin yung Q2 nila. Yung Q3, let's see, 8304, 3967. Yun na sila nag-iba sa Q3. So ang third vector from the numerical implementation of the classical Gram-Schmidt starts with a point 8304, while in this case, Q3, using the modified Gram-Schmidt in the computer, provided us with a 0.1753. So nakita nyo na kagad yung discrepancy, although on paper, dapat parehas sila ng ibibigay. And that's the problem with ill-conditioned matrices. You will lose significant digits due to instability of the matrix alone, but that loss of significant digit might be propagated in the rounding off at every step of the way. So nagpatong-patong na yung errors, not just from the instability, but also from rounding off at every step. So kaya medyo malaki na yung naging discrepancy when using the modified Gram-Schmidt, using the classical Gram-Schmidt process. All right, so you can play a little bit more here. Say if you want to consider, say, the 50 by 50 Hilbert matrix. So let's try that. So I just changed n to 50 from 5 to 50, or kahit 100. Oh. Okay. Hello guys. Nawala pa ako for a while there. Am I back?
Sir,
Yes.
Okay. So, saan ako nawala? Sorry, hindi ko nabasa kagad yung chat kasi nasa MATLAB window ako.
so you were doing already n equal to 100.
Okay, so pero nakita niyo naman yung discussion ng QM, QC, how they are different?
Opo.
Yes, sir.
Oh, buti na lang konti lang. So let's try 100. Siyempre, hindi nyo gustong gawin yung Gram-Schmidt ng mano-mano for 100 vectors, right? So let me reshare my screen again. Okay, there we go. So I just changed n equals 100 here. Then let me run it and see with just a click of a button, tapos na kagad yung Gram-Schmidt for 100 vectors. The problem here is kappa is now 4 times 10 to the 19th. So highly ill-conditioned na yung matrix natin, which is the 100 by 100 Hilbert matrix. The residual from the classical Gram-Schmidt process is 93.7559, which is huge. So ibig sabihin, malaki na yung nawala talaga. But you look at the residual from the modified Gram-Schmidt process. So ibig sabihin, 1 unit yung layo nung 100 by 100 identity matrix from test matrix C. And let's see if that is good enough. Of course, hindi na tayo maasa dun sa classical Gram-Schmidt. If you see the test matrix for the classical Gram-Schmidt, ang diagonal say 1, pero yung off-diagonal entries niya contains a lot of numbers and they are not even small numbers. They are 0.89, 0.9. So this is nowhere close to identity matrix, which we hope for. So ibig sabihin, the numerical instability caused us to lose the orthonormality. So hindi na orthonormal yung nakuha natin mula sa classical Gram-Schmidt. Kasi yung nakuha nating matrix QC ay hindi unitary. So na-defeat yung purpose ng pag-employ ng Gram-Schmidt using the classical approach kasi nakuha nating matrix hindi siya orthonormal at all. So that's crap. We can't just throw away the classical Gram-Schmidt. Pero there's a chance we get a good result from the modified Gram-Schmidt. From the modified Gram-Schmidt process, you see that there are some entries that are not that small. Halo-halo na sila. May 10 to the minus 6, 10 to the minus 7, 10 to the minus 8. Here you have 10 to the minus 16. Yung mga off-diagonal entries, dapat 0 sila lahat, diba? Because we were hoping test mat M will be close to the identity matrix. Pero yeah, in some applications, this might still be acceptable. Kahit meron ka ditong mga 0.11, 0.07, and so on. But yeah, but I won't rely on using this result in any numerical simulations that I'm going to do kasi hindi na siya ganun ka-reliable. Even the modified Gram-Schmidt process. So kailangan mo ng ibang numerical techniques on how to get away with this instability. So, and again, I kind of expected that because when I look at the condition number, the kappa value for the 100 by 100 Hilbert matrix, so 4.0740 times 10 to the 19th, and that is not a good number, right? Okay, so some other ways you can modify this actually, I think that's it. You don't need to modify this too much. Hindi required na gamitin yung GS at yung MGS with a Hilbert matrix. So you can just comment this out and then probably comment the computations of the residual out. Tapos pwede mo pa rin gamitin si GS kahit mano-mano yung A. So pwede mong i-comment ito. Tapos mag-input ka ng matrix A na mano-mano. Say, ano nga yung matrix na ginamit natin sa isang example? Let's see. Halimbawa, gusto kong gamitin si Gram-Schmidt. Say, kaya 1, 1, 1, negative 1, 0, 1, and then 1, 1, 2. Ito yung sa example 64 na vector. Okay. So remember from example 64, meron tayong vector 1, negative 1, 1, 0, 1, and 1, 1, 2. So gagawin ko silang columns ng matrix A, tapos papagawa ko yung Gram-Schmidt kay MATLAB. So kaya yung matrix A dapat ay 1, 1, 1, negative 1, 0, 1, 1, 1, 2, kasi yung columns niya dapat yung vectors galing sa example 64. So, and then, pwede ko pa rin palang gawin to. This should be n equals 3. Kasi 3 by 3 yung matrix natin ginamit. I-comment ko na yung Hilbert matrix kasi hindi naman matrix Hilbert matrix yung gagamitin ko. I'm going to use this matrix A that I inputted by hand here. Okay. Then I can enter it. Okay. And then the condition number of the matrix we got from example 64 is 12.778, which is fairly close to 1. That is 10 to the first power. So we will just be losing one significant digit. All right. And you see that the classic residual from from the residual from the classical Gram-Schmidt process is 0.7818, which is pretty small. So I'm guessing test match C is close to identity. And yeah, malapit nga siya sa identity except for the 1, 3, and the 3, 1 entry, which are negative 0.07818. Pero other than that, I'm seeing numbers that are of order 10 to the minus 16, so they are pretty good. And then, as expected, the modified Gram-Schmidt process will have near zero residual. Kasi stable nga yung modified Gram-Schmidt. And you see, this is the test matrix for the modified Gram-Schmidt. This is our test for orthogonality. So mukhang the modified Gram-Schmidt preserved orthogonality better than the classical one, which is as expected because we said classical Gram-Schmidt is the better way to do it numerically. And then let's see, ano yung QC and QM? So QC and QM are this, and I guess they are near each other except for the third element. So yeah, yun yung naging discrepancy nila. Pero again, theoretically, on paper, we should have gotten the same QC and the same QM. But again, because I asked MATLAB to do the calculations for me, you see, even if for a highly stable matrix, kailangan maging worry tayo about the rounding off errors that might propagate, especially when using the classical Gram-Schmidt process. All right. So you can play with this script, example 65. And I guess you can also use this to verify results for your homework. So if you permit me, maybe we can spend 5 minutes to look at one of the homework problems so I can explain it to you. Yes, sir, really, you have a question?
Sir, I'm just wondering, sir, yung dun sa implementation ng nung algorithm ng modified, di ba sir may yung number of decimal places na nag-save tayo, can we increase that sir, yung number of decimal places na gagamitin so that we can minimize the rounding off error?
Yes, you can do that in MATLAB. There are options in MATLAB that you can say you do double precision, which is 10 to the minus 32 yung magiging machine precision. So pwedeng up to 32 decimal digits. You can go to 64 to 128. Kaya lang, the expense is magiging matagal na yung running time ng algorithm kasi it will take some time for MATLAB to process it. But yes, you can increase it, but at the expense of longer computation times. Pero for us, we can just, because we are just illustrating instability, so you can stick to the defaults in MATLAB. So siguro, but whenever doing your own researches, you might want to look at these issues. So paramihin yung degree of precision, decimal digits. Pero yun nga, but given that matrix, we should expect to lose many decimal digits. So, but sir, really, you're right. So, pero kahit na sabihin mo 32 decimal digits yung gagawin ko, pag unstable pa rin yung digit, yung matrix mo, that will still cause problems even if you increase the degree of precision. You can try, but it's not guaranteed to solve the problem kasi marami pang issues in between na nagaganap.
Thank you, sir.
All right. Now okay. So sorry talagang overtime na, but I want to talk about lastly, yung sa homework na lang para you can start doing at least one homework problem before we meet again on Monday. Pero Sunday pala bukas, no? So yeah, take some time off tomorrow. It's Sunday. Ang deadline pa naman nito ay I think sa Friday or Saturday. Sige, double check ko na nga rin para I'll not be spreading fake news. So the deadline for homework 6 is on, let's see, tentatively it's on August 8th. August 8 pala yung deadline ng homework 6. So that's going to be Sunday next week. So I guess you'll still have lots of time to do it. But yeah, if you want to start, maybe I can show you. Yeah. So homework 1, problem 1, which is about floating point arithmetic. So in problem 1, you will be mimicking what the computer is doing. So mag-acting kayo dito as if you are a computer. Okay. Now, computers do a rounding off arithmetic, but in that arithmetic, all inputs are rounded off based on the number allowed by the computer. And then every after operations, you round off. So in this exercise, we will be rounding off. So ibig sabihin pagka ikakat mo na yung decimal digit, pag 5 and above, you round up. Pag 4 and below, mag-round down ka. So for instance, if you're using a 3-digit arithmetic or a 3-digit machine arithmetic, for the input pi, which is 3.14159264 and so on, okay? So ikakat mo siya to only 3 decimal digits. So ibig sabihin makakat ay simula dito, right? Pero the digit to be cut is 5. The first digit to be cut is 5. So we will round up. So pi in our arithmetic is considered to be 3.142. So ganun yung gagawin yung rounding mechanism, okay? And then in computers, this is what they do. So if they are asked to calculate this, okay? So gagawin niya bawat operation, pero nag-round up na siya sa bawat isa. So 1/4, no problem, it's 0.025. 1/3, so it's we know that it's 0.3 and so on, right? 3 decimal digits, so lang yung ikikip ko. So 0.3333333. First decimal digit to be cut is a 3, so we round down. So the disregard ko na lang to completely. So I'll have a 0.333 there. Same thing for 1/6. So that's a 0.166666 and so on. First digit to be cut is this 6 here. It's 5 or higher. So I will ignore this, but I will add 1. So 1/6 will be treated by our arithmetic to be 0.167. Okay. And then same thing goes for 2/3. So you get 0.667 there. Tapos ang gagawin nyo, gagawin nyo ito kasi by hand. So mangyayari, this is the first operation that you need to perform. So you multiply 0.167 and 0.2, say in a calculator. But the calculator might give you 4 decimal digits as your result. So, but at that point, you will round off and get 3 decimal digits only. And from now on, this guy will be treated as 0.033. So sa lahat ng calculation nyo, kakalimutan nyo na lahat ng decimal digits other than the 4th. So this means that I have an error here, nag-round off ako, so meron na lang 0.033 dito. Then I will go on with the rest of the calculations. And that's what I said. That machine errors propagate, or rounding off propagate. Kasi dun sa pag-encode ng 1/6, may na-round off na tayo. And then dun sa pag-multiply, ang ginamit ko ay rounded off na 1/6. Yun ang minultiply ko sa 1/5. So may additional error na naman doon. And then in the result, I am rounding off the result, which is erroneous to begin with, because this is not exactly 1/6, right? So rounded off, tas nag-multiply ako, yung result ni round off ko na. So this has 2 levels of error in it. Error in the truncation of 1/6, error in the multiplication, error in the rounding off. Tapos siya yung forward ko dun sa susunod na calculation. So kaya nagpa-pile up yung rounding off errors. Kasi at every step of the way, we are obliged to cut off. Kasi kung computer ka, 3 decimal digits lang yung alam mong i-store at a given time. And yeah, this is just an illustration of the process because in problem 1, I ask you to do or to use the classical or the modified Gram-Schmidt process to get the unitary matrix Q for this guy. Okay? So, ibig sabihin, ito yung unang vector, ito si A1, ito si A2. Kailangan yung gawin si Gram-Schmidt process. So, dalawang vectors lang naman yan of length 2. So, sana madali lang siya. Ang magiging siste lang dito is you will be doing a 5-digit rounding off arithmetic. So 5-digit rounding arithmetic. So you apply either the classical or the modified Gram-Schmidt process, but you need to round off to only 5 decimal digits every step of the way. So kaya medyo tatagal siya. Kahit 2 by 2 lang yan. So may makukuha kang Q1, siya yung gawin mong column ni Q, first column ni Q, tapos yung second column ni Q2. Right? And then kailangan yung computein yung test matrix and see how far off from being unitary is that matrix. Okay, so there are several more follow-up questions here. There are some details included in homework 1, but I guess you can start trying to solve problem 1, at least. Yung problem 2 kasi householder transform, which would be our starting topic for Monday. Okay? Hopefully matapos ko to. Doon nag-worry na ako. Sana matapos natin i-discuss yung module by Wednesday para you still have enough time to finish the homework by Sunday, August 8. And then for those who still have meron pang problems from previous homeworks that they haven't answered yet. So again, you only have until August 9 to completely submit them. So please schedule your time wisely, manage your time wisely. Though kakunti na naman sila, so kasi nakita ko yung iba nagpa-partial na, so I'll go back to grading later today. So try to read problem 1 in details. You'll see some more explanations there. If something is not clear, you can send me a message any time of the day. And if I'm awake, I'll try to reply as soon as possible. But yeah, you can try problem 1 for now. And I guess let's stop here. It's unhealthy to to talk more than 2 hours of mathematics a day. But yes, Miss Sao, you have a question?
Sir, question lang doon sa homework. So we'll just follow po what we did earlier. Sir, yung pang length, everything po when we do it, we just cut it off up to 5 decimal places. Even po yung length.
Good question. Yeah. Yes, please. Cut off even the length.
Okay, sir. Thank you, sir.
Para lalong mali yung makuha nating matrix Q. Because okay. I just want to illustrate in problem 1, ano yung nangyayari sa computers, bakit nagkakaroon ng problema. So pagpropagate ng error, especially if you're dealing with an ill-conditioned matrix. And the matrix A I gave here, I think actually is ill-conditioned. So kahit 2 by 2 lang siya, ill-conditioned siya. So hindi talaga siya ideal for machine implementation. Okay, so please, round off even in the computation of the lengths. Okay. Pero yung template ay pwede niyo na lang ipakita ang template ay yung sa template nung examples natin from above. So kahit wag niyo na ipakita yung step by step na rounding, katulad ng ginawa ko dito sa example, pwede niyo na lang siyang gawin on paper or gawin siya sa spreadsheet or sa calculator. But again, make sure you round off to 5 decimal digits after every computation. And yun yung nakikita kong complication, why problem 1 might take some time to finish. Kasi kailangan careful kayo pagka-perform ng operations. Hindi niyo pwedeng pagawa sa calculator na isang pindutan lahat. So kailangan niyo siyang step by step talaga. But I don't think it would be that too long because 2 by 2 lang naman yung matrix. So that should be fine. Okay, other questions? Okay, if there are none, thank you all for coming today. I wish you a good weekend. If you can, please take a rest tomorrow. It's Sunday. But if you need to, kasi last week of classes na, alam ko na maghahabol din kayo with modern algebra. But yeah, if you have any questions, just let me know. I'll try to answer it as soon as possible. I'm still behind answering some of the emails. Sorry about that, but I'll try to be updated with that. Ang utang ko na lang sa grading ay homework 5 problems 3 and 4 and the extra problems. So hopefully I'll finish that today and then I'll go on answer grading yung mga backlog questions niya over the week. All right, so thank you guys. Have a good day and see you on Monday.
Thank you, sir.
Thank you,